In this video, I want to speak to you a little bit about motion of objects on inclined planes. So an object can accelerate down an inclined plane, and that acceleration is dependent on our angle theta above the horizontal. Now, even though we're dealing with kinematics and motion without reference to the forces causing the motion, I absolutely can mention that we're assuming there's no friction on this incline. That's what is meant when I say negligible. We will neglect any frictional forces. So the acceleration due to gravity, or little g, is essentially broken into what we call parallel and perpendicular components, and those are with reference to the inclined plane. So a frictionless surface, this object will slide down, and its acceleration is broken into parallel and perpendicular components. So we describe the motion of this object as down and parallel to the incline. Then, if we were to do a free body diagram, we would see for this object that little g, the magnitude of the acceleration due to gravity, or 10 meters per second, is straight down toward Earth. However, the object's motion is down and parallel to this incline, raised some theta above the horizontal, so many degrees above the horizontal. So if you now resolve the acceleration due to gravity, or little g, that is going to become the hypotenuse. Little g is the resultant vector in this. And we resolve then into the parallel components. We can see that we get the right-angled triangle on the screen here. Okay, so this is pretty cool because this also lays a foundation for our next unit when we look at the forces that are acting on an object on an incline. And so I like to at least mention it briefly in this first unit because the idea is very similar. So we can now move that vector to show that that acceleration is down and parallel to the incline. Okay, let's look a little bit more at this here. So if we now consider our angle above the horizontal to be theta, I want you to consider the geometry in some of the angles here. Let's go ahead and look at that together. So we have a 90-degree angle here, so you can hopefully see a smaller right-angled triangle here within the larger right-angled triangle, and you're going to love what I'm about to show you. And so we have a 30, 60, 90 right-angled triangle in this smaller triangle within the large. And just follow me here. On the other side here, we have a 90-degree angle. Okay? And that means this angle is 30 degrees. This angle, where you see the arrow pointing to on the screen, is the same as this angle here. That's pretty cool. So the angle above the horizontal ends up also being the same as this angle here. And of course, this would add up to 180 here, which is where the 30 comes from. So I feel like it's so important for students to understand where that comes from. That's why I'm taking this time to teach you about it. So the 30 degrees is the angle we will use when resolving the hypotenuse or resultant vector into its perpendicular and parallel components, respectively. Let's go ahead and take a closer look at this. We're going to be using trigonometry. Let me go ahead and show you this. So I've just explained that this angle theta is the same as the angle theta of the incline above the horizontal. So regardless of what that angle theta is, this is how it will break down in our right-angled triangle. So we're going to end up, if we use trig, let's put our right-angled triangle here. This is our resultant vector, right? And that is our hypotenuse. And so we have our perpendicular and parallel components. So solving for the parallel component of the acceleration due to gravity, we get g sine theta. Likewise, for the perpendicular or adjacent side, here we get g cosine theta. Now, if you're not quite following that, let me show you here again. So g parallel is the acceleration of this object down this frictionless incline. That's a fact. So this is the acceleration down the incline. So it's not all 10 meters per second. I think you already know that. That's intuitive. That's common sense. But it is less than 10 meters per second. So that will be the acceleration. Let's look at the trig again here. Above my head here, you can see, so sine of theta, opposite over hypotenuse. Again, remember our angle theta is here, so opposite over hypotenuse. So we get our g parallel over little g. Rearranging to solve for g parallel, we multiply both sides by little g, and we get this expression here. And you'll have this memorized anyways. But what do I care most about? I care most that you understand where it comes from. So I wanted to take this time. Let's now look at this object here, which is on an incline, a steeper incline, say 60 degrees above the horizontal. And so if we wanted to actually put in numbers here, we would say g parallel, because that is the motion of this ball, is down in parallel, is equal to g, which magnitude of 10 meters per second squared, multiplied by sine theta. So if we use 10 meters per second multiplied by sine theta, we actually get the acceleration of the ball down in parallel to the incline to be 8.7 meters per second squared, which is clearly less than 10 meters per second squared. Now let's look at this scenario here. What's our angle here? 90 degrees. And you see where I'm going with this, because the sine of 90 degrees is equal to 1. So 10 meters per second squared times 1 gives us the magnitude of the acceleration due to gravity. So in this case here, the object's acceleration due to gravity is indeed little g. So in this video, we've looked at how you can look at the motion of an object on a frictionless incline, and then this can be used in our UAM equations denoted as an A subscript with the parallel component, the modulus bars there, indicating that it is the parallel acceleration. And now you know not only how to resolve little g into what we call parallel and perpendicular components, but you know how to solve for the magnitude of that as well. So we've continued now looking at our UAM kinematics topics, and I will see you guys in class.